Hey, hello physicists, what's the crack? So today we're going to look at interference of sound waves, okay? So what this question was talking about is that we have got two loudspeakers and they're both going to emit sound waves, and the student starts at position A, which is equidistant, right? It's along the midpoint line between the two loudspeakers, and as they move from point A to point B, it told us here the amplitude starts to decrease and then increase again. So what I would write in the test is at point A, I know they're going to hear a loud sound. Point B, they hear a loud sound. So between them is when it gets quieter again, okay? And it wants me to explain why this happens, okay? So my first bullet point is just explaining why it's loud at A, okay? So my first bullet point at A, the first point I'm going to say is because it's equidistance away, there is zero path difference, okay? So what that means is if I have a wave, D-I-F-F-E-R-E-N-C-E, sorry, spelling. If I have a wave and it leaves P and it goes towards A, and it leaves Q and it goes towards A, because that's the midpoint, those two lines, P to A and Q to A, is the exact same distance. So there's zero path difference between the two waves. The two waves travel the exact same distance, zero path difference. So at A, there's zero path difference. So what we say is that the waves are exactly in phase. Okay? What in phase waves means that if I've got a peak of one wave, it exactly matches the peak of another wave. They're exactly in phase. So we call in phase constructive interference. Okay? So what that means is when the two waves meet, when the two waves superpose, we're going to get constructive interference. We're going to get a loud sound because there's zero path difference. They're in phase, which means it's 360 degrees in phase. Another way you can see 360 degrees is 2 pi radians if you want a full circle, okay? And then the next thing we know, we just said from A to B, it's going to get quieter. And that's because if we get some point here, point P to that point is going to be much shorter than point Q to that point. Point Q to that point has to travel a further distance. So at B, or pardon me, not at B, between A to B, there is a path difference. So what that means is one wave has to travel further from one loudspeaker than from the other. So there is a path difference. If there is a path difference, when the waves superpose, which means when they meet, they're going to be out of phase. So because they're out of phase, that means they're not meeting with peak to peak. One of the waves is at peak and maybe the other wave will exactly out of phase. And what means they'll cancel each other out exactly, and you'll get destructive interference. Okay? And then it did finish off by saying it gets louder again. So we're just going to finish off our bullet point by saying at B, the waves again are going to be in phase with each other because their path difference, so even though this is a shorter line, the path difference is going to be a whole integer of the wavelengths. So let's say the wavelength of that wave was maybe 3 meters. So what this means is P to B is probably going to travel 6 meters, and Q to B maybe travels 3 meters long, so like 9 meters. There's a whole wavelength difference. So at B, we know again that they're exactly going to be in phase, or 360 degrees, or you can say 2 pi radians. So constructive interference happens again. Which is why they hear a loud sound. Okay? So that's my interference of wave, or my superposition of waves. Okay? So that's grand. Follow me for more physics content like this.